So we're going to continue working with limits. And limits are going to be a big part of Chapter 2 for us, building up to the derivative. Now, I guess what I would say in terms of rules with limits is the first thing you do with limits is try plugging it in. Try plugging in the limit. If it works, great, you're done. I'll tell you right now, I'll guarantee you that there's going to be some problems on the test, not a lot, but some where all you have to do is just plug in the limit. And that's all I'm looking to see. Do you understand that? Now, if you plug in the limit and it works, great, you're done. Now, I've already plugged this into my calculator, so let me switch screens here a little bit. Go over there. If I want to find that limit, well, let me just try and plug in the actual number here. Now, I've got some stuff left over from our last section. That's fine. And we're looking for the limit of this function as x approaches 2. Let's just plug in a 2 and let our calculator do the work. 18. Bam. You're done. So that's the nice thing about working with limits, is that sometimes evaluating a limit is nothing more than just plugging it in. 2. Now, if you plugged in a 2 and did 4 times 2 cubed minus 2 times 2 squared plus 2 minus 8, you get the same thing. Actually, it was 18, wasn't it? Yeah. 18. Done. Let's just check it on our calculator since we have that already set up anyways. So what typically I do when I try and look at a limit is I try and set the x value to be in the middle of my window. So x equal 2 would be in the middle of a window from 0 to 4 along the x-axis. So let's take a look at our settings here. Let me clear this out. Go to the window key, and I'll set x-min to 2 and y-min to 4. That way it puts my point of interest right in the center. And that actually has another advantage that we'll see in a little bit. The question is, well, what do I set my y-axis to? I don't know. I don't know what this fourth degree or third degree equation looks like. But the good news is you don't have to know. So follow me along with this trick. Hit the zoom key, and then you're going to type the number 0. I'll move over here to show you. Zoom 0 gives you zoom fit. It'll automatically adjust the y-axis so that it fits your graph. And it fits it perfectly. So if I hit zoom 0, bam, there you go. There's your graph. And it fits nicely in the window. Now you can use the trace key to kind of trace around. The nice thing about the trace key at this point is that it starts out right in the middle of your graph. And right in the middle is what you wanted to see. At 2, you're at 18. You can use the trace key to move a little bit to the left and a little bit to the right. If you move a little bit to the left, you can kind of still zoom in and get closer and closer to x equal 2, and you're getting somewhat close to y equals 18. But that point's right on the graph, so we're in good shape. The limit is 18. So nice. First order of business when you're trying to find a limit is always try plugging in the limit. If that works, great. If it doesn't, then you're going to have to look at other things. So for instance, the next function I want to look at is this one. The limit as x approaches 2 of x squared plus x minus 6 over x minus 2. Now, the one thing that you might be familiar with from your algebra classes is that when you have a term in the denominator like x minus 2, you typically get this crazy behavior with a vertical asymptote, where to the right of it, it goes up towards positive infinity, to the left of it goes down towards negative infinity, or vice versa. I could flip that around just by changing the sign there. But either way, you usually get some crazy behavior when you divide by something that's getting close to 0. And as x gets closer to 2, this denominator is going to get closer to 0. So strange things are happening. But when I look at this graph, I don't see that kind of behavior. It's kind of weird. It's like, well, wait a minute. Where's that crazy vertical asymptote behavior that we saw in the last one? This looks pretty well defined until, and I don't know if I can land on it just right, Oh, did you see it real quick there? At x equal 2, it's actually undefined, isn't it? So the graph doesn't exist there. But what about the limit? Does the limit still exist even though the graph is undefined at that point? Well, do a little thought experiment. Take a look at the limit from the left and the limit from the right. Are they going to the same place? Yeah. What would that value be? What's the limit from the left and the limit from the right going to equal in this case? You have to kind of read between the lines. Yeah, 5. Looks like it's going to 5. So what's going on with that? Well, let's take another look at this. So this function, I'm going to rewrite it. Instead of writing it that way, I'm going to write it as x plus 3 times x minus 2 over x minus 2. So, that looks kind of suggestive. What are you just dying to do at this point with that rational expression? What? So, yeah, we got it factored. Is there any simplification that's just screaming to be done?
So, x minus 2.
Awesome, perfect. Hey, you cross out the x minus 2. It's like, whoo, yeah, look at that. Cancellation, man, nice. The thing is, you can cross this out, but you have to remember, is that function defined at 2? It's not. So as long as x is not equal to 2, you can do this. And that's the big thing with this question here. It says, what's wrong with this equation? And what's wrong with this equation is that the left-hand side is not defined for x equal 2. But the right-hand side is defined. So, okay, all right. But do we need the function to actually be defined at this point in order for its limit to exist? The answer is no. We just saw that, right? We were looking at the graph, and yeah, the limit exists, even though the function is not defined at 2. There we go. Come on, at 2. But the limit still exists. So the nice thing that you can do for yourself in terms of calculating limits is a little algebra. You can do this. You can review you can factor this, cancel that out, and say, all right, well, we can still look at the limit. This limit and this limit are going to be the same. Now, let me see who was paying attention. If I wanted to evaluate this limit, what was the first rule of limits that I told you about? What should you do? Plug in the limit, yeah. That works pretty easy from here, right? Someone want to take out their calculator and do 2 plus 3 for me? All right. I'm thinking that's 5. All right. Nice. You're done. That's the limit. So that you can actually do that with that one problem we did in the last section too. It's just that the algebra gets a little bit more messy. You probably want to use Pascal's triangle to do 2 plus h to the 5th power. It'd be kind of messy. I don't even want to do that one off the top of my head. So, all right. Well, let's try another one. See if we can't get this one to work. We'll take a look at the limit as x approaches 3 of x squared minus 8x minus 15. Now maybe you were paying good attention in the last one and learned a lesson that'll help us in this one. As x approaches 3, is there anything I can do with this numerator? Yeah, it's going to factor. Good. In fact, you might go out on a limb and say, I wonder if one of the factors is going to cancel with its denominator. I wonder if they created it that way. And the answer would be yes. So you got it factored. Now you can cancel that out. And now we can look at the limit as x approaches 3 of x minus 5. That's a little easier to deal with. What's that limit? Yeah, negative 2. Just plug in the limit, right? 3 minus 5 is negative 2. And that's it. Beautiful. You're done. Nice. Now there's a lot of rules with limits that make things work pretty nice. But before I go on to example D, are we okay with example C? Some thumbs up from my homers? My zoomers? All right. Thank you. Let's keep going. Now, one of the things about limits is that the limit from the sum of the limits, or the limit of the sum is the sum of the limits. So this I could calculate as the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. Kind of like you're distributing the limit there in that case. And so on. This is going to work down here. With this is going to equal the limit as x approaches 0 of f of x minus the limit as x approaches 0 of g of x, and so on. The limit as x approaches 0, excuse me, negative 1, it should do down here. Negative 1 of f of x times limit of g of x. Basically, you pretty much be able to do what you think and want with limits, as long as you're working with a continuous function. Of course, we've yet to define a continuous function, but roughly speaking, a continuous function is something that can be drawn without lifting your pen from the paper. But let's take a look at the first couple of these. So I broke this up into two limits. Limit as x approaches 2 of f of x, and limit as x approaches 2 of g of x. So let's take a look at this first part. As x approaches 2, well, it's not just enough to just do this limit as x approaches 2. We've got to think of kind of two limits. The limit as x approaches 2 from the right and from the left. What's that limit going to be, or does it even exist? Well, as you approach from the left and from the right, what y value are both of these approaching? Negative 1, thank you. So negative 1. And let's go up to the function for g now. As x approaches 2 from the left and from the right, we're both getting to the same spot, which would be 2. Overall for a sum of 1. Beautiful. Why don't you try a couple? See if you can't do maybe the next two. I'm going to start learning some names. So, if you're watching this later, you can kind of fast forward this until I get rid of the pause button. This is my pause button. I know, it's pretty high tech, isn't it? Pretty cool. Okay, so let's take a look at these things here. Jackson, you were asking about this. Maybe you can help me out, or help us all out. In order for the limit of f of x as x approaches 0 to exist, what has to be true? What has to happen?
Both sides have to be intersecting toward the same point.
Yeah, the limit from the left and the limit from the right have to be equal. But that doesn't happen for this one, right? So that one's a does not exist. It doesn't really matter what happens here. If this limit doesn't exist, then overall that limit's not going to exist. So we'll just kind of stop reference there. Although if you're curious, actually, you know what? I was looking at the does not exist applies to g of x, right? G of x doesn't have a limit at 0. F of x does have a limit at 0, right? As you get close to 0 from the left and from the right, that limit is 2, but it's the g of x that does not exist. So overall, the limit's not going to exist. All right, thanks, Jackson. How about this one? Limit as x approaches -1 from of f of x and g of x. So let's start with f of x. As x approaches -1, which is here, from the left or from the right, that value is getting closer and closer to 1. How about for g of x? What's that limit as x approaches -1? As you're getting closer and closer to -1, what y value is g of x getting close to? 2. Thank you. All right, 2. And overall, the product is going to be 2. So again, nice. Let's keep going. This one, basically you're going to apply the limit of the numerator to the limit, or apply the limit of the numerator divided by the limit of the denominator. Let's see what happens in the numerator. As x approaches 3 from the left and from the right, the numerator is approaching 1. Let's see, 3, 1, 2, 3, yeah. Numerator is approaching 1. 1, 2, 3. Oh, okay, I see what's going on. What's the limit as x approaches 3 for the denominator? 0. And unfortunately, 1 divided by 0 is undefined, so this limit just does not exist. Yeah, it's not defined there. Let me go back to something I said a little bit ago, and that is, what's the first thing you do when you're trying to evaluate a limit? Yeah. Yeah, plug it in. Plug in the limit. Perfect, thank you. So we can apply that right here. This is going to be 2 squared times f of 2. So it's going to be 4 times f of 2. And hopefully that limit of f of 2 exists. Let's take a look here. As x approaches 2, so that's going to be right here, from the left or from the right, what's the limit? As it's -1. So 4 times -1 would be -4. And last but not least, f of -1. I like this. They're mixing things up on us a little bit. And the thing is, there's no limit with this. So Davidson, what's f of -1 going to be for us, please?
Looks like it's going to be 3.
Yeah, it's right up here. Notice that there's a hole here, so if you're looking real close, the value of the function and its limit are going to be different. So, yeah, that's going to be a 3 there. Good job. And Shruti, how about this one? The limit is x approaches -1 of g of x.
I said it was +2.
Positive 2. Yes, perfect. I agree with that. So for an overall limit of 5. Nice. Feeling pretty comfortable with those? Thumbs up? Yep. All right. Good deal. Thank you. let's continue. Ooh, a graphing calculator is recommended. Wow. All right, so it says graphing calculator is recommended. Estimate the value of this one. Are you guys getting the hang of the graphing calculator? You okay with some of the stuff here? Let's see if we can't try this with a graphing calculator in a couple different ways. So let's see here. Let's do this one. Let me clear out a bunch of stuff. Let's put in a new graph. And I'll clear out this stuff as well. So I want x, I'll start out with that, divided by, and I need parentheses, if I'm doing it kind of old school, if I don't have an up-to-date calculator, parentheses divided by the square root, so second and then the square key. You know, I forgot to hit the clear button so you can kind of follow along with my work here. 1 plus 3x. And then you got to exit the square root. So make sure you hit that right arrow to get out from underneath the square root. And then minus 1. I forgot to hit the minus key. What is that? Minus 1. And then a closing right parenthesis there. For those of you who ever going to computers, your parentheses always need to be balanced. If you have a left parenthesis, there has to be a right parenthesis. Otherwise, the compiler is going to give you a little hard time there. Okay, I think we're good here. Let's take a look at it with the graph first. Now, we're interested in seeing this graph near 0. So I want to put 0 in the middle of my window. So I'm going to hit the window key. And let's just pick something that's got 0 in the middle of it. So I'll go from negative, let's do negative 2 to 2. That's putting the limit, that x value, right in the middle of everything. Now, what was the trick to get the calculator to do the rest? Do you remember that? Zoom 0. Well done. Good job. That sounded like Austin. Thank you. So, zoom 0. And bingo. There you go. Let me clear that out. Maybe make that a little bigger. Now notice something funny about this graph. Looks like it's got a hole in it, doesn't it? Yeah. In fact, if you hit the trace key, probably reflects just as much. It says, yeah, x is 0, but I can't tell you what y equals because it's undefined. Going back to the first rule of limits. The first rule of limits is to plug in the limit. But if you try plugging in the limit here, you'd end up with what? You'd end up with 0 over 0. That's undefined. That's why your calculator is going to have problems with it. But does that mean the limit doesn't exist? Just because the function doesn't exist here, could the limit still exist? Yeah, it could exist. So let's see what that limit is. Now it's asking you to kind of estimate the limit. So if I hit the trace key, and I did, and go a little bit to the left, it says estimate the limit to 1 decimal place. It looks like it's getting close to about 0.7 if I was to estimate it to 1 decimal place. Okay. Well, let's see what else they ask us here. It says make a table of values for x getting closer to 0 and guess the value of the limit. So this is another great question. And every time I say great question, I'm trying to give you a big hint as to the kinds of things that I would ask on an exam. Let's make ourselves a little table. So I'll hit the second key, then the table key, or the graph key. I guess it depends on which one you want to think of it as. I'll get rid of this. Now, a sequence of values that get close to 0. Closer and closer to 0. So, we'll start out maybe at 0.5. And then I want to get closer to 0, 0.1. And then maybe 0.01. And then maybe, I don't know, any other suggestions? How about 0.001? I mean, I'm not really doing any rocket science here. I'm just trying to add more zeros and get closer and closer to 0. Of course, this one's going to show up in scientific notation. But you can start to see where the y values are going. And you can try that in the other direction too. You can go negative 0.5. It doesn't like that one. Negative 0.1. Negative 0.01. Negative 0.001. And so on. Oops. Negative 0.0001. Now I'm hoping that the y values are, starting to settle down enough that you can kind of guess what the limit is. If you need to see more digits, let me remind you, you can put the calculator or the cursor on this column and see as many digits as you could possibly want. So what's it look like this limit's getting close to? If you had to take a guess, a number, a fraction, what number? Yeah. Good. And what fraction is that? Do you recognize that fraction? Bad at fractions? Okay. Somebody help out Marissa. She was so good. 2/3. Yeah. 2/3. Yep. Perfect. Thank you both. So 2/3 would be our limit. All right. Now I think fortunately for you, they're just looking for a decimal answer here. But yeah, actually there's two parts of it. There's the decimal answer, and here's the rest of it, 2/3. All right. By the way, cute little trick here for you guys. And Marissa, I'm not picking on you, but I mean, you inspired this. If you're, suppose you're bad with fractions, you're like, oh, I'm just terrible with fractions. So like 0.375, yeah, I don't know what that one is, It's okay. I got your back. You hit the math key, and then you press enter twice, and it converts those answers to fractions for you. So that way you don't have to be super good with fractions. So nice. Okay. Questions or thoughts there? Still doing all right? Let's keep going. It says, find the limit if it exists. Well, this one should be kind of interesting. Again, it's going to be another question of graphing things. So let's start by entering in the function. I'll clear out my function from the last one. And I'll clear this as well down here because I want you to be able to follow along with my keystrokes. The one thing that you might have difficulty with on something like this is finding the absolute value. So let me help you out with that part. We're going to start with parentheses around the numerator. So parentheses 2x plus 14 divided by parentheses. Actually, you know what? I don't want parentheses. I want the absolute value there. So to find the absolute value, go to the math key. And then cursor to the right across the top to the number column. And then the first option there should give you the option for absolute value. Now, depending on how up-to-date your operating system is on your calculator, it might just show up as ABS. It might actually show up as the absolute value symbol. It just kind of depends on how up-to-date your operating system is. And then x plus 7. Enter. Nice. So, was everyone able to manage to get that in? All right.
Explain the absolute value one more time.
Sure. So one more time on the absolute value. Actually, let me do it a little different way, but also doing your absolute value here for you. Let me just remind you of that trick. If you hit the alpha key and then the y equals key, the first option here will let you draw a fraction up and down. And that gets rid of the need for those extra parentheses in the numerator. So if you're like not a big fan of those, you can work around it. Now in the numerator, I can just type 2x plus 14. Whereas before, I needed to put parentheses around, so I'm not just dividing 14 by everything, I'm dividing the whole numerator. Now I can get around that. But as far as the absolute value, back to your question, you hit the math key, then you go to the right once. And it's the first option there. Just press the enter key or type the number 1. The first option there allows you to do the absolute value, x plus 7. Let's see. We wanted to look at this function near x equal negative 7. So I need to set up a window around that. Can anyone suggest to me some values that I could use to set up a window around negative 7? Yeah. Perfect. Thank you, Tim. And what Tim did in suggesting negative 9 to negative 5 is he gave me a window that was centered at x equal negative 7. And that's key. That's really important because it's going to help you spot things later on. Now the rest of this, we'll let the calculator do that. I'm going to hit zoom 0, and I get this kind of strange graph. Now, if you're looking at that going, well, that's not really helping me out much, one thing I can do is I can change the window on the y-axis just a little bit, just to see a little bit more. So instead of going from negative 2 to 2, let me go from negative 3 to 3, just to see a little bit more of my function. So with those changes, I should be able to hit the graph key. By the way, one more thing here. When you type in a negative number, like negative 3 or negative 9, make sure you use the opposite key on the bottom of your calculator. If you get an error, chances are maybe you use the subtraction key to enter something like negative 9. There you go. So there's my graph. Oh, kind of weird. It's either 2 or negative 2. So, Now, in looking at this, if I give you a problem on the test like this, your response, and I don't know if it has to be written or not, but what you really need to do is look at the limit as x approaches negative 7 from the left of 2x plus 14 over the absolute value of x plus 7, and the limit as x approaches negative 7 from the right of 2x plus 14 over the absolute value of x plus 7. And let's take a look at what those limits are. Now, as we approach from the left, I believe that was negative 2. And as we approach from the right, it was positive 2. Is that what we want to see when we're trying to calculate this limit? Michelle, what's that saying about our limit? Michelle, isn't it? Oh, I'm sorry. Oh, thank you. Michelle, thank you. So what's that say about our limit? They're not equal, so overall, what should I write here? Because these two things are equal or not equal, what should I write for that limit? Yeah, thank you. Does not exist. Limit from the left, limit from the right have to be equal in order for that limit to exist. And that's not the case in this one. So you're stuck. All right. Now, I'm going to lay the groundwork for stuff that we're going to do later on. And this is going to be the squeeze theorem. So this is the formal stating of the squeeze theorem. But what I want you to do is draw any graph you want. It's kind of sandwiched in between these two lines. So, and I want you to draw it all the way to 0 from the left and to the right, but draw any graph you want as long as it's between those two lines. Now turn to a neighbor and do the following calculation. Take a look at the limit. Let's see, what do you want to call this graph? Call it f of x. Limit as x approaches 0 of f of x. Calculate that for yours and for neighbors. My Zoomers at home, if I had a little more time, I'd put you in a chat room here, but this is just kind of a quick example here. So go ahead, turn to a neighbor, calculate these limits. Of course, if calculating those limits, you really need to look at the limit as x approaches 0 from the left and from the right. From the left of f of x, and the limit, let's see, limit as x approaches 0 from the right of f of x. Now you're free to draw your own functions, right? But everyone should still be reaching the same conclusion. What conclusion is this? Where do those limits go? Where do they have to go? They have to go to 0, right? Because there's squeeze between these. These are going to 0, and anything squeezed between it also has to go to 0. There's just no choice. So the limit from the left and the limit from the right, both of those should be 0. And that's really the essence of the squeeze theorem, is figuring out what those limits are. So, all right. We're going to need the squeeze theorem later. It's going to help us calculate some strange stuff like this. The limit as, let's do theta approaches 0 of sine of theta over theta. Now, if you try your number one tool for calculating limits, plug in the limit, what do you get when you plug in theta equals 0? Yeah, 0 over 0. So is that 1? Is it infinity? Is it undefined? And actually, spoiler alert, you can actually show that this limit is 1, despite the fact that both the numerator and denominator are going to 0, which is strange, but it's true. Let's finish up with some algebra. So up till now in this class, what we've done is we've done a couple different approaches. We've looked at things numerically, we've looked at things graphically. We're going to get our hands dirty with some algebra to solve these last few problems here. So let's see. We'll start with this one because it's the friendliest one. And I know that you might look at that one and go, I'm not seeing too much friendly about that. But it is actually the friendliest one of the remaining bunch. So let's look at the limit. Limit as x approaches -2 of x plus 2 over x cubed plus 8. Nice. Nice. Let's see. Carrie, at home. What's the first thing we try when we try and evaluate a limit? What should I try first?
Plug it in.
Yeah, plug in the limit. Excellent. Excellent. Alexandra, if I plug in -2, what would I get? Let's work in the numerator. If I plug in -2, 0 over 0. Oh. Now that's not saying that the limit doesn't exist. But what it is saying is that you're going to need to do some work to figure out what that limit is. So if you notice, I didn't really start out this class with a lot of review. What I like to do instead is give you just-in-time review. Just kind of like all the manufacturers, the big three, have just-in-time shipping and this, that, and the other. Of course, during the pandemic, it's not exactly worked out too well, but in any case, just-in-time stuff for us right now would be this, a reminder about factoring. A plus B cubed actually does factor. Now the way I like to share this is that you start out with what you cube to get each of these. You cube an A and you cube a B. By the way, one thing that is sure to really make your instructor happy, and I hope you appreciate my sarcasm here, is if you do that. It's just not that. Sorry. It's not even close to that. Take the first letter and multiply it by itself. A times A, that's A squared. Let's take the second letter, B times B, B squared. This is a trinomial, so I need to do something different to get the middle term, and what I'll do is I'll just take A times B. Yay. So I'm looking good, except I don't have the signs that I need here. And the signs that I need here follow this acronym. Same sign, opposite sign, always positive. So, what would that mean for this problem? Well, same means same. Plus and a plus. Opposite, that would mean a minus here. And the last one would be a positive. Yay. Now the cool thing about this is that this idea works even if you have the difference of cubes as opposed to the sum of cubes. So it would be A, B, A squared, AB, B squared. And Sonny, maybe you can help me fill in the blanks here for this one. That's like I said, that same acronym works. Same, opposite, always positive. Go ahead.
A minus B, A squared plus AB, and then AB plus B squared.
Perfect, perfect. So minus, plus, plus. Notice that in each of these formulas you have exactly one negative sign. One negative sign per customer, I like to say. All right. So what does that have to do with this problem? Glad you asked. Let's take a look here. Limit as x approaches -2, x plus 2 over x plus 2 times, well, let's see. You're going to take x times x. That's going to be an x squared. 2 times 2, that's going to be a 4. Can anyone tell me what that middle term is going to be? Well, the middle term is going to be this times this. Yeah, but we generally write it as 2x. Thank you, gentlemen. Yusuf, what signs go in here?
So x squared minus 2x plus 1.
Perfect. Minus and a plus. Perfect. Why did I go through all that? I mean, it was quite a diversion and quite a lot. Why did I bother going through all that? What did that give me? Yes, thank you, Nicole. So at this point, you get to take out your favorite Zorro pen and go, ole, and cancel those out. Jeff, retire that one. Thank you. Let's try this one again. There you go. Those cancel, and that was the problem. That's why when you plugged in the -2, you were getting 0 over 0. Is because those terms go to 0 when you plug in a -2. Now, however, this becomes the limit as x approaches -2, of 1 over x squared minus 2x plus 4. Now, I'm thinking we're going to have a little bit better time calculating the limit now because we got rid of that problem. If you were actually graph this, it would technically have a hole in the graph right at that point. That's what you would see. All right. Well, I did all that work. I got rid of that x plus 2 term from the numerator and denominator. Now what? How do I finish this? Tim? Yeah, plug in negative 2. So it's going to be 1 over negative 2 squared minus 2 times negative 2 plus 4. I think it's going to be 1/12. Nice. Now, how could you confirm that if you go, I'm not sure if I factored that right. I just don't know. How could you confirm that if you wanted to? If passing this class was actually really important to you, you wanted to know before you hand in the test, did I get it right? How could I figure that out? Rohan, any ideas? Plug it into the original function? And do what? Well, what if we looked at the graph? Could the graph tell us maybe? Or maybe a table? Let's take a look at it with a graph or a table. Now, I realize not everyone has a graphing calculator. So let me show you how to do this on Desmos. So let me do this. I'm going to type in f of x equals, and then it was x plus 2, and I'll highlight this, divided by x cubed, hit the shift key and the up arrow, x cubed plus 8. So you can kind of look at it numerically here with tracing on the graph, but what I really wanted to look at was some values. So I want to f of, say, 0.1. And there you go. F of 0.1, 0.12 or 0.262. How about 0.01 or 0.001? 0.0001. And I'm not liking my result. I'm wondering if I made a mistake in my algebra. See, it's good that we're checking things, right? Yeah, let's see here. Negative 2. Oh, okay. Yeah, there we go. All right, let me go back here. So yeah, we're approaching negative 2, right? So something close to negative 2 would be f of negative 1.9 or 1.99, 999. And maybe you're not really good with fractions, but you can take and do this. You can do 1 divided by 12 and say, oh, okay, yeah, it looks reasonable. I'm getting close to that decimal value. So you can have confidence in your answer by looking at it. You can also look at it graphically. Let's just zoom in. And, graphically, you can get pretty close to negative 2. It's undefined at negative 2, but a little bit to the right of that, a little bit to the left of that. Yeah, those both seem to be reasonable. Now, I think it's harder to do it with the graph for this one, but you can certainly do it numerically. And of course, you can do a t-table with your graphing calculator as well. So, does anyone want to see me review that, or are you getting comfortable with the graphing calculator? Comfortable? Thumbs up with the graphing calculator? All right, that's good. Nice. All right, so let's keep doing a couple more here. These are the challenging ones. What I did here in selecting these was try and give you a good variety of different things that you will see as you work through your homework. So let's move on and do another one. Let's see. Which one do you want to do next? This one? Yeah, sure, why not? Let's take a look at that one. Okay, so before I do this one, let me give you a little reminder. Do you guys know how to cube this out? 6 plus h cubed is not 216 plus h cubed. If you write that, just leave it blank. All right, just skip that because it's just way wrong. Now, as a reminder how to cube those things, let me remind you of Pascal's triangle. And Pascal's triangle starts out with a 1 and then a 1 like this. And you keep on adding 1s on the outside edge, but then in this inside, it's 1, 2, and 1. So you're adding the 2 above to get the 1 below. And I'll start with a 1 here, but if I add these two coefficients, 1 and 2 gives me a 3. 2 and 1 gives me a 3. And then a 1 here. And now what are these coefficients good for? They're good for finding the coefficients of, say, a plus b to the 0, a plus b to the first power, a plus b to the second power, and then a plus b to the third power, and so on. Let's actually do one last row here, just to remind you. What would this next row be? Start out with a 1 here. What should I put here? 4, 6, 4, and 1. These rows are always symmetric. I mean, I could spend literally a 4-hour class talking about all the amazing properties of Pascal's triangle. Like if you were to actually add these up across rows, they're always powers of 2. Down this diagonal, so the next one would be a 10 down here. You'll find your triangular numbers, like, 3 is a triangular number, 1, 2, 3 more dots, 6, 1, 2, 3, 4, 10. Those are all your triangular numbers down there. It's just amazing. But the thing we need it for is this one right here, is cubing this out. Because when you cube that out, you're going to need the coefficients. It starts out like this. Starts out with a to the third, and I'll leave some space for coefficients. And then a to the second, a to the first, and then a to the 0, which we don't necessarily need to even write. And then b to the 0, b to the first, b to the second, and b to the third. The coefficients that go in here are exactly from Pascal's triangle. So it would be a 1, a 3, a 3, and a 1. Your alternative to using Pascal's triangle would be to multiply it out like this. A plus b times a plus b times a plus b. And then keep track of like terms, add them all up. What's something to the 0 power? 1. So I'll just get rid of those. I put them in there so you can see the pattern. These exponents always add up to this exponent. 3 and 0, 2 and 1, 1 and 2, 0 and 3. Overall, you should get a cubed plus 3a squared b plus 3ab squared plus b cubed. It's a lot faster than doing this stuff by hand. I wouldn't. I mean, I can, especially for these, but anything higher than 2, I'm going to be using Pascal's triangle. All right, so what does it have to do with this one? Well, in the numerator, I've got a limit that involves the cube of a binomial. So I want to calculate the limit as h approaches 0 of 6 plus h cubed minus 216 over h. Chris, what's the first thing we try when we work on a limit? Plug in 0. Perfect. Thank you. Plug in 0. So if I plug in 0, Kaylee, what happens when I plug in 0? I get 0 over 0. Bummer. So what that means is I have to do some algebra. I have to get my hands dirty with this problem. Now, there's going to be some problems on the test where I just say find the limit. Some I'm going to say show the algebra. Some I'm going to say look at the graph, etc. There's 3 different ways we're discussing today to look at and get at a limit. You should be able to do all of them. And that, in this problem, would mean expanding this out. So, let's see. How about if I do that as a kind of a separate little problem here, and then we'll come back and plug it in here. So, I want 6 plus h cubed. So I'll start out with the 6 cubed plus, and then leave some space here. And that's going to be 6 squared times h to the first power plus, and again, leave some space. And then 6 times h squared, and finally h cubed. And that's part of it. But I need to plug in the numbers from Pascal's triangle as well. So I got a 1 here, a 3 here, a 3 here, and a 1 here. So let's see. That's going to be 216 plus 3 times 6 squared. That's going to be 108 plus 108 h plus 3 times 6 is 18 h squared plus h cubed. Nice. Let's keep going. Let's take that expression and substitute it into our limit. See if we can't simplify and figure things out from there. So let's rewrite that as the limit as h approaches 0 of h cubed plus 18h squared plus 108h h plus 216 minus 216 divided by h. Okay, so let's see here. Did that help us out any? Is there anything about this expansion, all this work we did, that helped us out?
You can get rid of 216.
Yeah. Hasta la vista. 270. 60. No. 16. 216. Yeah, 216. In any case, we get rid of the 216, and that still doesn't cure our problems. We took a look at the limit as h approaches 0 of h cubed plus 18h squared plus 108h divided by h. If you plug in the h equals 0, you're still going to get 0 over 0. Yeah, suggestion over here. No, no, it's not, because the cube here was on the outside. So it's not like I had a 6 cubed and an h cubed. I had the whole thing cubed. So it's a good question. What you're asking about would have been is if I had 6 cubed minus h cubed or 6 cubed plus h cubed. That would be different. No, you can't distribute. So it's a good question, and I'm glad you're asking it, because it's really tempting. It looks like you should be able to just say, oh, well, that's 6 cubed plus h cubed, right? Oh, okay, then what are you saying? Oh, I see what you're saying. Oh, treat this as the difference of cubes, the whole thing? Yeah, that's actually really clever. I don't know how many people would like to do it that way, but yeah. No, that's really clever. If you can do that for you, I mean, I can see exactly what you're saying. That's great. That's outstanding. There's nothing wrong with that. If you did it that way, I'd be happy to see that on an exam. So what he's saying is treat this as the difference of cubes, kind of like what we had with our previous one. So that would be your A and that would be your B. So you'd have 6 plus h is your A and then 6 is your B, and working things as the difference of cubes that way. Yeah, nice insight there. That would work. It eventually is going to get you to the same place we're going to go here. All right. So one way or another, you've got to get here. This isn't quite far enough because we still would be left with h over h. But here's the last trick. Limit as h approaches 0 of h times h squared plus 18h plus 108 over h. And what was my trick here? What did I do? I just factored out the h, right? Now the h can cancel. Now we're left with the limit as h approaches 0 of h squared plus 18h plus 108. Let's see, who haven't I picked on yet today? Luke. What would I get for that limit?
Maybe 108.
Yeah, excellent. Just plug in the limit, right? So at this point, we got rid of the problem of the 0. So plug in the limit, we get 108. And you're done. Nice. Thank you, sir. Excellent. Excellent. 108. How are we looking on that one? Pretty good? All right. 2 more, and we're going to be done with this section. But what I'm giving you in all these different problems is different examples of the kinds of stuff that you're going to see in the homework and could see on an exam. So if you're not sure about something, reach out and ask me. If you have a question, please get it answered. All right, so we've done these 2. Let's try this one right here. So I want to look at the limit as h approaches 0 of the square root of 9 plus h minus 3 over h. Javier, what's the first thing we should try? Yeah, plug in the limit. Does plugging in the limit work for us on this one? No. Still stuck with that 0 over 0 stuff. Yeah, kind of, oh man. All right. Now there's a different trick in this one yet again. And so let me show you the trick, and then we'll go back and apply it. But you end up with 0 over 0. So basically that's saying you need to do some algebra. Now our trick in this one goes back to this. If you had a minus b and you multiplied it by a plus b, something special happens. You remember this one? Can anyone do this in their head? Let's take a look at what we get. You get a squared, remember FOIL, plus ab minus ab minus b squared. And something interesting happens here. Those terms disappear. And what are you left with? You're left with a squared minus b squared. Wow, okay. So you get the square of these terms, and the middle part cancels out. That's the trick we're going to use in this one. Let's see how it works. All right, so we do the limit as h approaches 0 of the square root of 9 plus h minus 3 over h. Let me put parentheses around this. My trick, well, the only thing I really can do is multiply by 1. That's the only trick I got. Multiply by 1. The question is, what form of 1 am I going to use? And the answer goes back to our trick. I'm going to look at this as being a minus b. And if I multiply by a plus b, nice things are going to happen. So what would a plus b look like over here? It's going to have to be in the same. It's going to have to be the same for the numerator as it is in the denominator. So it's going to be the square root of 9 plus h plus 3 in both the numerator and denominator. All right. Now the idea here is to really use the trick. All right. I could FOIL this out, but it'd be a lot of work. And it'd be messy work. And I don't really feel like doing that. So let's see here. What else could I do? Well, I could use the fact that I'm going to end up with a squared minus b squared. So this should be the limit as h approaches 0. Now in the denominator, I'm going to leave everything factored. I'm just going to leave it as h times the square root of 9 plus h plus 3. And you might ask, well, why? Why aren't you distributing it? That's a good question. And the answer is because this isn't my first rodeo, all right? I've taught this class for quite a few years. I know what's going to happen. So I'm just going to leave that there for the moment. But in the numerator, let's see what happens. I'm going to get a squared minus b squared. So what's it look like when I square a, this expression? What would I get? When you square the square root, what happens? It cancels, right? So I'll get 9 plus h. What do I get when I square the 3? Oh, come on. Come on. 9. That wasn't a trick question. 9. Yeah, there we go. So you get the 9. And as before, you see, oh, you get some cancellation here. And the thing that really gets your problem rolling comes right here. h over h times the square root of 9 plus h plus 3. Is in this step right here. What is it that's going to help us actually calculate this limit? Anyone? Come on, we're one problem away from our break. Help speed this along. What can I do now? Yeah, let's get rid of the h. The h was the problem. I mean, notice if you plug in an h equals 0, you're still going to have a problem here with this problem. So if we cancel out the h, now we've got the limit as h approaches 0 of 1 over the square root of 9 plus h plus 3. Wow. Finally looking a little bit better there. Justin, what's that limit going to give us, please?
1 over 6.
Perfect. Square root of 9 plus 3 is 3 plus 3, or 1 over 6. Nice. Now, on your calculators, you'll get nice, good decimal values that are getting closer to that. But unless you're really familiar with, numbers and stuff like that, it's hard to look at this and do, oh, yeah, let's go into 1/6. At some point, you're going to need to do the algebra. And there's going to be, a number of problems on the test where I'm going to say, hey, I want to see that algebra. And this is the kind of work that you're going to be doing for me. Okay, last one. Any comments or thoughts on this one? You saw the big trick on that one, right? The big trick was to make sure that you multiply by the conjugate of that term. And don't distribute that h in the denominator. So the last one is this one right here. 3 plus h to the negative first minus 3 to the negative first over h. So kind of a tricky one in terms of just really understanding it, what it's looking at. So let's do it. Limit as h approaches 0 of 3 plus h to the negative first power minus 3 to the negative first power over h. Okay. Let's understand this negative first power stuff first. What does it mean when I have something to a negative exponent? How else could I write 3 to the negative first power, for instance? Yeah. Awesome. Thank you, Austin. So 1 over 3. Just put it in the denominator and make it a positive exponent. And I'm not going to write 3 to the first power there. But we're going to do the same thing here. Now the difference is that negative 1 applies to this whole binomial. So it's going to be 1 over 3 plus h like that. So that's really what it means. Perhaps a little bit better look at it. And no surprise, if you plugged in the limit, you'd end up with 0 over 0 again. So 0 over 0 is not saying that the limit doesn't exist. It's simply telling you that you got work to do. All right, that's all it's telling you. So, in fact, you want to look at this one with a table first and see if we can't guess what the limit will be? All right, let's do that. Let's do a little table work just to see if we can't guess what the limit is, and then confirm it with some algebra. So let me go here, clear out the old fractions. This one's going to be a little bit more of a pain to plug in. I'm going to do with an extra set of parentheses in the numerator. So parentheses for the numerator, and then parentheses for the first binomial. We'll do 3 plus x parenthesis. And then a quick way to get that negative 1 in the exponent is right here on the left-hand side. Bam. Right there. X to the negative first power. You can do 1 divided by 3 is fine. You can do 3 to the negative first power. That's also fine. Whatever works for you. Divided by x. And I want to take a look at this as x gets closer and closer to 0. So once you've got that expression in, let's go to our table, second, and then the graph key. Let's delete a lot of this stuff. And we'll start out with 0.5, 0.4. Yeah, let's just jump ahead. 0.1, 0.01, 0.001. And maybe it's not as dramatic as we might like yet, but let's do one more, 0.0001. I'm getting 0.1111. Probably not a number that's jumping into most of your minds at this point. So we will look back at that and see if we can't make sense of it. But for this part right here, we have to figure out what we're going to do. The problem is we got to get rid of that h in the denominator, otherwise we're always going to be stuck with 0 over 0 somehow. And here's the trick. 1 over 3 plus h minus 1 over 3. In the numerator part of this, we need to get a common denominator. So right now, I've got two fractions with different denominators. So I need a common denominator. The LCD is going to be 3 times 3 plus h. That's my LCD. So for instance, right here, I'm missing a 3. So I'll write this as 3 over 3 times this. What should I multiply the second fraction by? 3 plus h. Thank you. And let's see what that gives me. That's going to be the limit as h approaches 0 of 3 over 3 times 3 plus h minus 3 plus h over 3 times 3 plus h. And that's kind of nice because now I can subtract the numerators. And it might be looking real messy, like, oh my God, where is this going? So let's hang tight and see if we can't figure that out. The numerators have common denominators. So limit as h approaches 0. It's going to be 3 minus 3 plus h all over that common denominator, right? I'm tempted to write LCD just so it just doesn't look so bad. Do I write LCD or should I just write out the common denominator? It doesn't matter to me. All right, no takers. So 3 times 3 plus h. But that helps me out a lot right there. Can anyone see what's going to happen? Tim? Perfect. Now the one thing you have to be careful about in terms of canceling out the 3's is that that h is going to end up with what sign? Negative. Thank you. So this is going to be the limit as h approaches 0 of negative h over 3 times 3 plus h over h. And if you're kind of curious what happened in the numerator, let me just kind of show you off to the side here. That's going to be 3 minus h, because that negative has to distribute itself to both terms. And when you do, the 3's cancel out, and you're left with that minus h right there. You're still stuck with that same problem. You still have 0 over 0 if you tried to plug in the limit. But now we're in a better place. Let me help things out by putting a 1 here. May not seem like putting a 1 there makes a big difference, but it does. It helps us out. Helps us figure out what to do. Because when you divide by a fraction, what's the trick? What do you do when you divide by a fraction? It's the same thing as multiplying by the reciprocal, right? So I'm going to regard this as a fraction. I'll have a fraction in the numerator, right here, and a fraction in the denominator, right there. So this is the same as taking negative h over 3 times 3 plus h and multiplying it by the reciprocal here, which is going to be 1 over h. Wow. Finally, light at the end of the tunnel. And it's not a train, which is good. The h's cancel, right? So then what? Then I'm left with the limit as h approaches 0. The negative didn't go anywhere, so I'll have negative 1 over 3 times 3 plus h. What would that limit be? Jack? What would the limit be? Negative 1/9. Excellent. And now let's go back and check something. So I'm getting this number here, negative 0.111111. Let's compare that to negative 1 divided by 9. Negative 0.111111. Does it look convincing? Yeah. If you look at our table values are getting closer and closer to negative 1/9 numerically. And you're also seeing the same thing when we did it algebraically. So one confirms the other one. And that's a great thing. You can check yourself before you hand in these problems on an exam. You can say, all right, does that make sense? So I strongly encourage that you do that. Any last minute questions on this one? Or any of these in this section? All right. Yeah, question.
Do you want us to write the limit of h to 0 every time we move to like a new part of the problem?
That's a great question. Yes, yes. If you notice, I've been consistent in doing that as I did things here. Writing limit as h equals 0, limit as h equals 0, all the way through until this last step, right? Because without that expression, a lot of our steps may or may not be true anymore. So you really got to be careful. I mean, it'd be tough for me to give you a general rule as to when you could or when you couldn't. So in absence of that, yeah, keep this notation of limit around until you're all done. It's actually a big problem for me. I kind of know what you're doing, but at the same time it's wrong if you're writing a lot of this stuff without writing limit as x approaches this or h approaches this, etc. I'm like, all right, do I want to be a jerk? Or how much points should I take off? It's with a heavy heart that I look at that paper like that and go, what do I do? You know. So do me a favor and just write it that all the way through. That way I don't have to, even think about, how many points I want to take off. So yeah, thank you. And I'm not trying to be mean by that. It's just some of these things, some of these statements that you write without the limits are just going to be wrong without the limits, and it's tough for me to work on. But thank you. All right, anything else? Okay, good.